So we introduced a new lecture series in IMSA, TWAS, and IMSA. So it's very tempting for me to ask who are the members of TWAS in the room, but I'm not going to do that. So I know that Sir Michael Attia was Philippines member, Jack, many others. But in any case, it certainly is an organization that has honored many wonderful mathematicians, and we are going to work with them to benefit from their immense collection of talents. And today we have Jaqueline Mesquita from soon to be in Union County. And Jackie, of course, is a decisive force in our scientific advisory board with the enormous energy of the dynamo. She definitely helps use a lot. And she is a recipient of the L'Oreal Prize in mathematics. She's president of the Brazilian Math Society. And in 2 days, she will be the president of Malta. So, so she's a very distinguished scientist who is involved in many ways, not only in our scientific support, but also helping in different institutions in Europe and collaborating with some of our faculties throughout the state. So now let me let you know the only Jaqueline Mesquita, who is going to tell us about general concept of periodicity. Jackie, please.
Thank you very much for this very nice introduction. I'm very glad to be here again. It's a great pleasure to be in Miami. So first of all, I would like to thank very much IMSA and especially Professor Ludmil, because it's very important all these efforts that IMSA is doing for our countries in Latin America. So Brazil, that's my country, benefits a lot from many programs from IMSA. So I would like to thank a lot for all these programs, because it's really important to consolidate the mathematics in Latin American countries. So thank you very much for all those support. And here are some pictures. Yeah, so we had a meeting here in the University of Miami with many presidents of the Latin American mathematical societies to discuss about the future of mathematics in Latin America, and it was really good. Professor Ludmil brought together all these presidents of many countries in Latin America to discuss this, and also the prize that IMSA has. So it's really important for Latin America and for the mathematicians to encourage the young researchers and also the senior researchers. It's really important. So thank you very much. I'd like to start thanking all those efforts for the Latin American mathematicians. So I know that everybody is really tired. We had a very full day today with several lectures, and things are not exactly in the field of most of you. I will try to introduce a little some tools for my topic to not be too technical. So here are some co-authors that I will talk today about some works that I made together with them. So Professor Martin Bonner from the Missouri University of Science and Technology in the United States. Professor Sabrina Trebeck from the University of Pittsburgh University in the United States. Also Professor Henriquez. This is in memory because he passed away. But he was from Universidad de Santiago de Chile, and also my former PhD student, Amy. So today I try to talk about all those core words and yeah, some things related to them. So it's together with those collaborators. So everything started about this problem when we were available in a conference. And the question concerning how to define periodicity on time scales appeared in that time. So we started with that question in that moment. This is in Poland. And then also we continue working on that in researching pairs in Oberwolfach in Germany, trying to find a concept that we could unify the periodic function for all time scales. I will bring a little more about time scale theory, what that means, and why it's difficult to have a concept of periodicity on any time scale. But it was an open question in the field. So here we met for this research affairs program, and we made a lot of advances in that theory. So here with my collaborators have been Spraker in Overboard. So let's see what's about time scale counting. So what that means. So here it's a very recent theory. It's from 1988, and it was started with the PhD thesis of Stephen Hilger, and here Bernard Albach, his advisor. And here, one thing that's important, the main goal of this theory is try to unify the discrete and continuous case. So usually when you're working with different equations and some models, we know that sometimes you work with different equations considering the domain with the integer number sets or the natural number sets or different types of time scales. And sometimes it's important to consider the continuous, which means like the time in R that we know very well about differential equations. But sometimes, depending on the model that you want to describe, it's important to consider your model in a different time. And for example, the integer number. And this theory comes in the way to try to unify differential equations, and all types in between. So when you have like hybrid types, like continuous and discrete at the same time, or only discrete, so for example, quantum scale, you can have many different types of time scales. And the main idea behind it is to try to unify those theories. So the definition of a time scale is only a closed and no empty subset of the real numbers. So we can have many examples of a time scale, including, for example, the Cantor set can be a time scale. So we can have many different types of time scales, and we can model many types of phenomena using these different types. So in order to be able to talk a little about these, I need to introduce some concepts, but I will try to be not so technical, but only to bring some ideas concerning this unification. So first, we need these two operators that appear. We have the whole operator, and also we have the sigma operator. The whole operator is the background jump operator, and we have that the definition is the supremum of the point time scales such that it's smaller than t. And the other one is the infimum of the points in the time scale such that bigger than t. So we have here the two jump operators, one for route and the other one back route. And here we have the gradient function that's the difference between this for route jump operator and the identity. So this is the difference. And okay, depending how you have your definition, your relation with the points, we can have the definition of the point. So we say that if our sigma t is equal to t, we say that t is a right dense point. And also we will have about right scattering if sigma t is bigger than t, which means like isolated on the right side. Also whole of t equal to t is less dense. And if the whole t is smaller than t, we say that t is left scattering. So using that, only to bring, we can see that the definition of the derivative is very similar to what we have usually for the continuous case. Yeah, here if you have, for example, that your sigma of t is equal to t, we have exactly the derivative that everybody knows. However, here you also can have the derivative for the case of the discrete case, which means, for example, when you are in the discrete, we have here, like, if your time chaos that we denoted by the integer numbers, what usually we have as derivative is like an operator here, and so we say that this will be x of t plus 1 minus x of t. And this will come from this definition. And then it will change depending on your time scale, but this definition can unify all those types, including one that is very important to us, that we will see here. That's this one here, that's the powers of this Q, when you have a Q bigger than 1. And this will be very important because this brings the quantum calculus and has a lot of applications for quantum differential equations. So then we have the definition, and then here only for notation, because you will see that it will appear with F sigma, that will be this composition F with sigma, that sigma is the for-all jump operator that appeared before. And here it's important to talk what will mean for us isolated, because we will also work with isolated in some context, because you see that in order to bring the definition of a periodicity for all time scales, we needed to first investigate that for isolated time scales, and then we realized how to define it for all different time scales. And here the isolated will be all the points that are right scattered and right left scattered at the same time. So then we have many properties, the same way as we have for the continuous case that we learned in calculus, yes. So, but here, of course, with unifying things. So the main thing behind of this theory is like unify all those cases in order not to divide something in continuous, the other one in discrete, another one in hybrid. You can have all of them together. And then we have many these of properties that we usually have. We have here also, but a little different. But it coincides what we have for the continuous when we have that our time scale is the real number set. And here, other thing that's really important is that including our exponential function will be different, because it needs to coincide with the exponential function when we are in the discrete case that usually is a product. So we need here also to have that. And in order to have that, we need to introduce a class of functions that's called regressive functions. And this is very important to have some operators that make sense when we deal with this new type of exponential function. And then here, a function will be a regressive function if we have that this is different of 0. But if you see, when you are in the continuous case, yeah, the case that the real number sets, this mu, if you remember, is the sigma t minus the identity. And the sigma t is equal to when you have dense. So this mu of t is 0 in the real case. And then, of course, you always have that 1 is different of 0, which means that in the real case, we have that all functions are regressive functions. So you don't need to ask about it. However, if you are in other types of time scales, when you have that this mu can be other things, you need to ask this difference of 0. So then we have that the set of the regressive function is given by this R here. And here we needed to introduce a new operations to make sense that if you sum two functions, the sum is regressive, and also the same for the subtraction. And then here we need to use the circle plus addition and also the circle minus subtraction. So, but if you see the case for the continuous, the real numbers, the mu is equal 0. So you have exactly the comma that we have for the usual case. And then here you have exactly the same for when you have the subtraction. So we have the same definition when you have the continuous case. So here is the definition of the exponential function, and we define it the same way as we define the usual exponential function. But here you see again depends on the derivative, and our derivative will change depending on your time scale. You see? So here we have the problem, but using this delta derivative, that's the delta derivative that unifies. That will be this one here when you have your time scales equal the integer number sets, and will be the usual one when we are in the real numbers. So you have different types. And this will be our exponential function, the solution of this problem. And then we will have many properties concerning this exponential function, including a type of a semi-group property of exponential function. But here it's really important to mention that our exponential function can be negative. And it does not happen when we have only continuous case. Yeah, but here it can happen. So depending on your time scales, you can have strange situations for your exponential function because it could be like a product. You can have different types of definition depending on your time. And here is a type of variation constant formula for a type of problem. So if you have this problem, you can rewrite your solution in this integral form, the same way as we have usually for the continuous. But here, using this unified concept of exponential function. So, okay, so why is difficult to define a periodic function in this context? So probably you're asking why that's difficult. And the main thing is the following. So if you try to see how we define a periodic function, we see that usually a function is had omega periodic if we have this equality usually for t belonging to the domain of your f. So let's see if you are in the time scale, you should have this. However, here we have one problem. Since you are dealing with all time scales that can be any closed and no empty subset of the real numbers, you cannot ensure that t plus omega belongs to your time scales when t belongs to your time scales. Here it's okay. However, here you don't have that. For example, if you have your q equal to, you can have, for example, if you take, for example, omega equal to, you will have that, not always you will have here that inside. Or if you have a 1 or 3, let's say it's worse. So you have much more complication. So this here is a very strong property in our case. Since we're dealing with any closed subset of the real numbers. So we can have many ones, and most of them does not have the additive property. So, and we would like to have something that we do not need to restrict ourselves for this additive property. And then we try to find which would be such a type of definition for periodicity that we could encompass all those types of time scales. So this was like an open question in the field. So then, first they started with this one here. So Warner and Shoshan, they started with this here, that's the quantum case, to see how they could define the omega periodic function that thing. And they define it in that way here. So we say that the function is omega periodic if we have a this equality. It seems a little strange because of this multiplication. Yeah, if you see, however, it has this property property that usually we have for all omega periodic functions that preserves this integral when you do the integral in this size of the interval. So you have that it continues the same. We have these properties for the periodic function, and that's why it is defined this way. So here are some examples of periodic functions in that sense. So here bring this example, but just to show that it remains constant. The area that you have behind of your solution when you consider exactly this type of interval. So here you can see geometrically what that means. So that's why it's defined that way. So we are really in trouble because we need now to unify this definition that you saw here that seems to be very different of this one. We need a definition that in a quantum case is that, and in integers number set is that one. So we were many years trying to find something like that. And then, okay, we started with some ideas. And then first we decided to see only the isolated time scales, which means that all points are isolated, like right scattered and left scattered at the same time. But in order to do that, we first need to introduce what we call it iterated shifts. So if you remember before, we had that sigma that appeared as the forward jump operator, that the infimum of the point on time scales such that bigger than t, okay? So here, what we will have, we will iterate, we will compose this sigma omega time, okay? And we will denote that by this mu. So mu will be the composition of sigma omega time. And then here, if you see, for example, if you are in the integer numbers, we have that our sigma t, since that the infimum, if you remember, this is the definition, the infimum of the point in time scale such that bigger than t. So if you are in the integers number, the sigma t is t plus 1, okay? So if you do that omega times, if you compose that omega times, it will be t plus omega, okay? However, here, if you see, if you are in the real numbers, your sigma t will be equal t. So if you compose that omega times, it will continue be equal t. So you don't move. That's why we started with isolated, because in that case you have here, you have different ones. For example, for this time scale that we have here, if you see, the definition of that are the powers. So here it's like this type of powers here. And then the same will happen. So the sigma t, since that the infimum of all points in time scale such that bigger than t will be the next one, that will be qt. Yeah. So if you do that omega time, then we have here q to the omega t. So we have that one. So, and that's why we started with the isolated, because the sigma go for all. So you go it's not equal t, but it go bigger than t. So then we have here this sigma omega that we iterate. So we will use this notation. This mu will be equal the composition of sigma omega time. Then now we can define the periodic function on isolated time scale. In our definition is given by the following. So it will be the derivative of mu, that this omega times the composition of sigma, the derivative multiplied by your function composed with your sigma, and this is equal to. If this is valid, so we have that a function is omega periodic only for isolated time scales, you know, because for the continuous, it's not true. Yeah, because for the continuous, you have that your mu t is equal t. in that case, in the continuous. So we don't have that for continuous. So here, if you see, it coincides with all the isolated that we know. For example, if you are in the quantum case, we have that the periodic function exactly what we had before. So here, the mu t will be q to the omega t, and the derivative will be exactly q to the omega. Then we have the equality. The same happens for the hc. Yeah, so you have for the hc that your sigma t will be exactly c plus h. Yeah, so and then we have that appears with the omega when you do that composition omega times. And the derivative will be 1 in front. So that's why it does not appear here. And the same one for the integer. So we have that all cases we can cover with this definition. But then, okay, we would like to have also the continuous case, yeah, because the continuous is really important. We know many models that are really important for us and are described by different equations. So we need that for continuous case. And then how to have, for example, when you have both, like a continuous and discrete at the same time. Then we found one possibility for our definition to encompass. Then first starting with the continuous, what we realize is the following. So if we have a function, you can say that a function is periodic with respect to nu, and now nu is only a differentiable and a strictly increasing function, only that property. And then we have that if you have a inequality, we say that a function is periodic with respect to nu. And if you see, we have in our case, usually how you say the continuous case. If you take your nu t equal t plus omega, yeah, that's the usual, you have the derivative is 1, then you have an f of a t plus omega equal f of t. Then you have this property satisfied. So this is great because we have this for continuous and for all time scales. Here we made for this continuous, I only wrote it this way, but you can easily pass this to generalize to all time scales, only changing now to delta, to the derivative for the time scales. But now, instead to be your sigma, omega, your mean, it can be only any strictly increasing function. And this is a strictly increasing function, then that's okay. So we can have it for all those cases. And then we can see many types of examples, including, for example, okay, we do not need to ask that our f is continuous, so our f does not need to be continuous. And in that case, also we can have that the dirichlet function is a type of omega periodic function. If you take omega as rational, so you can have that it will be. And also here, we have that the constant function also will be, you have that it will be a periodic function if you take your t equals 0 or your nu equal t plus t. So if you take that, we have that. Also here we have different types of functions that's not periodic in the usual sense, but since here you can have different types of functions, you can have different notions of periodicity. So here your function f, the exponential function that's not periodic in the usual sense, is in that case periodic with respect to this nu t, that's the logarithm of this function here. So we have this possibility here too. Well, so we can have many examples here for cosine and sine. So our function that will be t plus 2 pi. Yeah, that's the usual one. So we have, again, the definition of the periodicity. And also we will see that we will have almost all those properties that we want about the integral. Did you remember that the first idea that we would like to have is to preserve the integral, yeah? So we have the same properties definition that will be very important to us. So here, if you define your f nu equal exactly that integral that goes from t to nu t, you have that first, you have the derivative here, and then you see this is exactly when you have your f is periodic, so it will be 0, which means that this integral here, this f, will be exactly a constant, that f. So we have exactly the property that you want. So here that's exactly saying that. So you have this is preserved, this property that we would like to have. And then here again, using this strange example, you can see that in fact, you have that this property concerning your integral will be satisfied. Yeah, so we have exactly that for the specifically nu t. So that's periodic in that sense. And we have that this property concerning the integral is satisfied. So here again, we have this property that is very usual that we see, yes, but usually we see a plus omega, and then we have fallacy. And also we have that if the same way as if a function is omega periodic, it's also 2 omega periodic. So here it's almost the same. If you have that nu is periodic with respect to nu, is also periodic with respect to mu composed by mu. So we have also those properties. And here the proof is very simple, and that's why I put here, but it's not simple to see. And okay, we will have many other properties concerning the sum of 2 new periodic functions. And when you do that for the time scales, we need to work with the regressive function. So we need to work a little more with those class that we had. But here, since we are on the continuous case, we have the usual sum to talk, and then we have the sum of 2 functions, 2 new periodic functions is a new periodic function. And then here also about the product of 2 new periodic functions. So we have that not necessarily is a new periodic function. Okay, so these are some about the definition, yeah. But we made some applications of those results for the averaging principle, the periodic averaging principle, to see if it would be like useful in that context. And we saw that it would be very useful. And then here we have a periodic averaging. So let's see. First, what is periodic averaging principle? So usually we have this original equation here that usually it's hard to solve because it's a type of nonlinear one, you see. And then we have the averaging equation. And the averaging equation is a simple one because if you see, your f0 does not depend on t. You have a f0 that only depends on y. And usually it's easier to solve this type of equation than the other one. And how you define this f0? Your f in the first equation, the original, is t periodically in the second variable. And then you have this f0 is exactly 1 divided by the period, and multiplied by the integral that goes to 0 to this period, and your s. And what do you have from this averaging principle? You know that the solution of the first problem is very close to the solution of the second problem when you have that your epsilon is very small. Or if you think that when you have the time very big, when you have the time goes to infinity, you have the solution that is going very close from each other. And why this is nice? Because you have a very difficult problem, and sometimes it's difficult to solve that. And you know that the solution is very close to the solution of the averaging equation that's easier to do. And then if you want to, let's say, to know if a solution is stable or if a solution has such a type of behavior, since you know that both are very close from each other when the time goes to infinity, you can know about the asymptotic behavior of your solution for the original problem, only investigated the behavior of your solution for the varied equation. So that's why it's so nice. So, okay, we decided to apply that for our specific case, that's for the new periodicity concept. Then here, it would be something like that. So here we have our original equation that you can see above. So it's exactly the same, but here we have the delta that we had before. Yeah, that's the derivative in any time scale. And then the averaged equation is given by t, and now appears here this mu t. However, if you are in the D, this mu t is equal 1. So that's okay. But of course, sometimes it depends on t. But then you have that separable, you have that t is a separable variable, then your function that depends on y. So that's why also it's easier to do with that. And then here, our f0 now is given by this one here, and your f is now periodic with respect to nu, okay? So now you have that your f0 will be 1 over omega, where you have this type, and then you have this integral here, t0 to nu, t0 and your x. And then here, an example, just to show. So here, if you consider any isolated time scale, which means that could be the integers number sets, the naturals, also the quantum scale, any of them, then you have that this type of set that's like a Ti, when I belongs to B, and then you have that our sigma T I will be the next one because you are in the isolated time scale. And this one needs to be bigger than Ti. And then if you define your f in this way here, so define this here, and then using that Ti is equal to Ti plus 2, we will have that this function will be in our sense omega periodic function. So here actually two periodic functions. And then using the definition, this is our mu because we are composing sigma twice. And then delta, that's the derivative, and then our f, and in the second one we put our nu that we had before. That's exactly sigma composed with sigma. And then using those properties concerning the time scales, we have exactly the same here. So because we have the property concerning this derivative, that quotient here, and then using the fact you are in isolated time scales, we know that the sigma twice Ti will be Ti plus 2 because you are in isolated. Yeah, so we have that. And then using the property, the definition of your function, we have a equality here. And then we have since we have that Ti is equal to Ti plus 2, we have this other equality here. And then we can check that in fact this is equal, and then your f is 2 periodic. So we have that. And then we can calculate our f0 to find our varied equation. Yeah. So here our f0 is given by this from the formula that we had before. Yeah. So 1 over 2, this integral here from our f. But then using the definition, I don't know. Yeah. Now let's come back. Using the definition of our f0, we have this integral here, and then we have that the definition of our f, we have exactly this equality here. And then using, actually first using the definition of our integral. Since you are in an isolated time scales, we have the integral is a sum. And that's why it appears this sum here. And then now using the definition of our f, we have this other equality here. And then what we have is that our varied equation is given by this one. And then we prove it, the theorem that for all cases that you constructed this way, we have that both solutions are close enough. And then we make some numerical simulations to check that. So here, if you see this asterisk in blue is the same equation. So we have these squares and also these asterisks, and we can see that they are very close from each other. Yeah. So this asterisk is the solution for our original equation, and the square is the solution for the averaged equation. And then taking epsilon, very small in blue, and in red, not too small. And we can see that it's not so close as the other one when you have a smaller epsilon. And here is that for this time scale to 8D. Okay, so we made for different time scales and considering different epsilons. The same here, but here we take HZ with 8 equal 0.5, and here we take H equal 1. That means the integers numbers. And then again, we have this composition. And if you see in the beginning, you can see that the solution, including the red, it's more far away. But then when you come from with the time, you see that the solutions getting approach from each other. And here again, HD, but using a different one. So H equal 1 plus 1.5. So in that case, again, we have that one very close from each other. And here we have this one, that's this quantum case. And here taking our Q equal 1.1, because our Q is bigger than 1. And then again, we have the same. We can see that they are very close from each other. And especially when you have that epsilon, it's very small. So you have, they are more close from each other in the case of the blue. And here again, the quantum, but for this other one. But again, we can see that's too close from each other. And then here also for the powers of the natures. So again, if you take our P equals 0.5, we also have this approach here. So in the beginning, not so many, but then if time is going, and then it's come to be closer from each other. Okay, so these are some parts that I think it's, I only try to put here. Okay, I think now it's okay. Yeah, okay. So this is like this part of the periodic function was something that it was completely open, and we have many other open questions that I'd like to bring because I think it would be very nice if we could solve this type of problem. One of them, since I know that many people here works with polynomials, one question that's completely open in the theory is about how to define a polynomial for all time scales. We have that for some time scales, and we have that Professor Victor Kach. He proved it for the quantum case, the definition for the polynomial, and using as a definition for polynomial concerning the derivative. Yeah, so here we use it, the derivative as our, let's say, the definition for the polynomial, because we wanted to rewrite, like to have a formula for Taylor's series. And because we wanted to linearize our problems in differential equations and to approach the solution of the original problem with the linearized problem. So to have that, we need to have an extension in Taylor series. And we needed to know what is a polynomial for all time scales. But it is a completely open question in the field. So we don't know for all time scales how to define in a consistent way polynomial using the properties concerning the derivative. Also, another open question that seems to be very simple, but nobody could have. It's like how to define a logarithmic function for all time scales. Again, it's not easy. we need to be careful because depending on the situation, we could not unify. So we needed to have something consistent in order to unify for all time scales. And this is again another thing that's completely open. Also concerning fractional derivatives. We know that many people is working with fractional derivatives. However, if you try to find a unified way to have that for discrete, continuous, hybrid, or quantum case, it's not possible until now, of course. But nobody could find a way to have that. And next steps in the direction, okay, there are many open questions in the field that I think it's a recent theory when we compare with mathematics, let's say this theory of unification is from 1988, so many questions in that sense, how to unify those questions or those concepts in order to construct a solid and unified theory. It's not that easy. So there are many open questions in the direction. And concerning these things about the periodicity, so we have now this concept that unifies the periodicity for all time scales. However, we know that for the continuous case, we have more general types of definitions and concepts than only periodic. We have, for example, almost periodic functions. And we don't know how to define the almost periodic functions for all time scales. Again, it's a completely open question, and I would like to invite you to also think about that. And more general than almost periodic is also almost automorphic functions. And again, we don't have any definition in that direction. We have for the quantum case, we have for the discrete case, and we have for time scales that have additivity properties. However, we don't have for any time scale. And it would be really important to have that. Yeah, so we have this type of problem. Also, for example, one thing that is still an open question is about semigroup theory. Because usually for the semigroup, when you define a semigroup, you ask a type of additive property. Yeah, you have, for example, just very quickly, you have here, you say, one of the properties of a semigroup is that this is equal this and this. But then here again, you don't know if you sum 2 points in your time scale, if it's still inside. And there are other ways to try to do that. We made a definition from the Laplace transform in order to have this definition because we have a Laplace transform for time scale. However, we don't have more than that. We stopped on this and made some properties, but many classical results we could not have in a unified way. So there are many open questions that I leave to you to think about.